Okay, good morning, physical science class. Today we are going to go asynchronous. So I'm going to lecture on free falling body, on the law of gravitation, and some Newton's laws. Let me share a screen with you. I will be able to explain what I'm driving at. So here is a topic on motion, no? Which is again taking up these three topics, which is part of our lesson, and we understand that this guy probably that is sitting here is the famous guy Sir Isaac Newton, no? And as we know, Isaac Newton formulated a lot of these laws, including the laws of motion, which is covered by three laws, and including the law of gravitation. So this morning we'll try to understand them, no, as we discuss it. No? We are now on motion. No? So let's start with the law of gravitation. So there's this law of gravitation that tries to explain why some planets in our solar system have a greater force of gravity compared to other planets, no, or maybe a celestial body, no, like a satellite, like the moon. No? Why does the moon have lesser gravity than the Earth? No, again, the reason why I'm saying that the moon has lesser gravity is that we notice that the moon does not have an atmosphere. No? By virtue of that, by that analogy, that the moon has no gravity, has no atmosphere, that its gravity must be lesser. No? It cannot hold the air, and therefore, it does not have any atmosphere. No? So the surface of the moon is basically very rugged from a constant bombardment of meteors, no, that strikes its surface. No? So, however, the Earth is not like that. No? The Earth is covered by air. There's an atmosphere that protects it from intruding or meteors that will just immediately strike the ground. No? So, if that's the case here on Earth, no, then I think a lot of people would have died, no, if there's no atmosphere that protects us from these meteors that falls, no, from the sky. No? So let's start with the law of gravitation. So what affects this degree of gravity, on our planet? So one is the sheer mass of the Earth. No? So planets with bigger masses, no, tends to have greater gravitational force. No? So again, so gravity always exists between two bodies. No? So a book and a chair, no? There must be gravity between them, no? If you put them side by side. No? However, the question is why don't we feel, or why is it that we do not notice the gravity existing between objects like a chair and a book? No? The reason for that is their mass is very small. No? Just imagine comparing that to a planet. So the mass of a chair is incomparably, very insignificantly so small, that we don't actually notice the force of gravity. So again, the mass affects a lot, the degree of this gravitational force. Now again, greater masses would mean that there's greater gravitational force. No? Now another factor that we can also talk about is the distance between the objects. No? If objects are, or if planets are near each other, then their degree of gravitational pull would be greater. No? As you move them further apart, then that force of gravity that exists between them will become lesser. No? So it means that the sun compared with Mercury, so since Mercury is the closest planet uh, on our solar system to the sun, then that gravitational pull will be much greater. No? So if it happens that Mercury will be moved further from the sun, then that force of gravitational attraction will become lesser. No? So as you move it further from another object, the degree of the gravitational pull becomes smaller. No? So in terms of distance, the force of attraction due to gravity is inversely proportional. No? So while the mass, no, is directly proportional to the degree of the gravitational force. No? So in terms of one equation, there's this G value that is equivalent to something like 6.67 times 10 to the negative 11. No? And you can find this value in some other slides that we have, no? Here in our canvas. No? So again, no, the ratio or the degree of the force is directly proportional to the product, no, of the masses of the two objects divided by the distance between them. No? So that's how the law of gravitational attraction, no, is determined. No? So we have this law that was first formulated by Isaac Newton. No? So this is one famous law, and we see this now in some other concepts in our physics. No, but we with a very similar expression. No? So again, that's the law of gravitation. No? So every particle in the universe attracts each other. The gravitational force is directly proportional to the product of the masses of the particles or the objects, no? While it is inversely proportional to the square of the distance between these considered objects. No? Let's go on a freezing body. So again, the reason why objects go to the ground is that there's that force of gravity. No? The force of gravity, of course, is invisible. We don't see it. We usually call it as a non-contact force. No, you don't have to touch, or gravity does not have to touch the object in order for it to be influenced by gravity. No, so they consider it as one of the non-contact forces. No, and I believe there are other non-contact forces like magnetism, like the force due to the electrical force. No? So they act at a distance. However, there are also contact forces that exist in nature that you really have to be pressed, no, like tension, like compression. They have to act, no, directly or touching the object, no? So they are called contact forces. No? Now again, now falling bodies are a result, no, of the acceleration or the force that is due to gravity. No? Now this value or this acceleration due to gravity is a constant value. No? So in terms of meter and second, that value is equals to 9.8 meter per second square. No? And it is always directed downward. So there are expressions that say that this gravitational force, no, is considered negative. No? There are those that write this as a value G, no, equal to negative, no, 9.8. No? So they write G as a value which is directed downward. No? And they write it with this expression. Again, considering that its direction is always downward. No? So you'll never see an object that is thrown, no? Uh, that the direction, no, of your weight, by the way, no, is always downward. No? So our weight will never be pointing up. No? So again, no, the reason why we have weight is that there is the action of gravity. So those are some results or effects of gravity. No? So our weight is one. No? So again, in terms of magnitude, that's the value of the acceleration due to gravity. No? And I'm going to erase this, no? So this will not disturb your view. And again, this value, acceleration due to gravity, no? If we hold, for example, an object, no, at a certain height, no? And of course, when you hold it, there's no velocity there. So we call the initial velocity v sub I as initial velocity to be zero, no? Because it does not move. Now, when I'm going to hold that object and then I'm going to release it, no? I'm going to now let it fall down, no? They notice that on the very first second, no? 1 second after that, no? They notice that the velocity changes from 0 to 9.8 meters per second. No? That's just after traveling for 1 second. No? If you let it fall for another one more second, and of course it's not an equal distance, no, because the object now tends to get faster, no. Now the second time you'll measure the speed of the object, it becomes 19.6. So you'll notice that it doubles, no. So if you double 9.8, it becomes 19.6, no. And again, no, as you let it fall again and let it drop for another one more second, maybe the distance there will be a bit longer than the first two. And now the speed of the object after the third second will become 29.4 meter per second. And then you'll notice that the speed increases on a regular interval. So if you get the difference is equivalent actually to what we call the acceleration, since acceleration is described as the difference in the velocities per unit time, no? So if you subtract the two velocities here, no, 19.6 minus 9.8, you'll get this constant value. So this constant value is known as acceleration. But in this case, we call it as the acceleration due to gravity. And what do you notice? That acceleration value is constant all throughout, no, the fall, no, of the object literally. No? So there is a constant acceleration in the falling, no, of a particular object. No? So we call this as, this type of motion is also called as uniformly accelerated motion. No? So we have an object that literally goes downward. No? Now, you would also probably realize that this condition may just happen, no, for maybe, no, situations where an object falls, no, relatively nearer the ground. No? But if we move it further up, no, like we move it 1 kilometer up, no, then this one will no longer, no, be true, no, because again, there's air that is present in our atmosphere. No? Now, air will cause the object to, no, to slow down. No? There's air friction that we call, no, or um, there's the opposition of the air, no, as the object falls down. So this one will not literally, no, be be experienced. No? So, for example, I'm going to hold a feather, and there's a metal ball that I'm going to hold. No? So if I'm going to hold them together and I'm going to release them at the same time, you realize that the feather will now drop relatively slower compared to the metal ball. No? So they will not fall exactly now with the same acceleration. If this is true, then they will reach the ground together. No? But if you're going to remove the air in between them, then you'll notice that they will reach the ground together. No? So again, no, the presence of air, no, causes things or objects, no, not to fall on a regular basis. No? But if we will remove this and we'll put them in a vacuum, then this will be true. No? Again, no, Neil Armstrong was able to prove that, no, when he stepped on the moon. No? When he was there on the moon, he was able to observe, no, that two things he dropped, no, on the surface of the moon, and he was able to achieve to make them reach the ground, no, together. No? So because again, in the moon there's no atmosphere, no, there's no air there. No? Okay, so the effect of uh, gravity, no? So it is uniformly accelerated. Now, what are the factors that affect the gravitational acceleration? One is latitude. No? So latitude means if you are from the equator and you go, no, to the poles, no, so the lines that you see, no, from the equator going up are called the latitudes. So there's less gravity near the equator, no, than when it is on the pole, no, because I believe the equator is much thicker, no, because the Earth is kind of oblate spheroid, as they call it, no? So it bulges near the equator. So the the distance, no, from the equator, from the center of the Earth to the in the equator is much longer. So there's less gravity in the equator compared to the ones in the poles. No, so the poles is much closer to the the center of the Earth. No? So because the Earth is not a perfect sphere, no, so it's oblate. So it's much thicker on the equator. No? Now next is the altitude. No? So if you throw an object on a higher uh, place from the ground, so as you move up, then there's lesser gravitational pull as you move upward. No? So maybe we can think of higher places like mountainous areas, but that's not a very significant height. No? So maybe you have to really go up, the sky, in order for the object to really have a substantial height. No? So higher altitude has lesser gravitational pull. No? And then next is the kind of surface. No? So water, soil, and rocky areas. So for more massive and more complex surfaces, like a rock or soil, then there's greater gravitational pull on those places, rather or compared to places that are no, not compact, like water. No? So water surfaces like the sea or the huge lake, probably there's lesser or considerably lesser degree of the pull of gravity. No? Now, for our equation on the free falling body, so if the body is considered to undergo free falling, like you hold it and then you release it. So initially, we consider that its velocity is zero. So the working equation that we have is simply this one. So we will multiply gravity, which is 9.8, and multiply it with time, and we'll be able to get the final velocity of the object. So if we will determine as well its distance traveled, then it's merely equals to gt square over 2. And again, we can do some transformations of the expression. So there are three expressions that we can use when we deal with objects that are undergoing free falling body. So again, free falling is when you hold and when you release it. It's also true when something falls, like you put a flower pot on a window sill, like near your window, and for some reason it tipped over and it falls. So that may be considered also as a free falling body because nobody throws it downward; it simply falls on its own. So its initial velocity will be considered zero in that case. Now here are other equations which we can see. So again, this slide, by the way, you can see this in our canvas. There's a slide that you can view and download there, which is about this one. So let's try this sample problem now on our free falling body. So an object falls from rest from a 600-foot GMA tower. So the first thing, now we will try uh, to answer letters A, B, and C in this one. So it's a 600-foot tower, and that's the only given here. And we'll notice that in order for us to solve, actually we have to identify three known values. But in this case, we simply have one value, which is the 600-foot tower. So again, this is probably considered as a free-falling body, so maybe we can use this equation. So we'll try going into this one. So let me use a whiteboard. So allow me to. So how do we do this? So again, let's try a whiteboard. So we have now a 600-foot tower. So our given. So the height is again, height is 600 feet. And then you have, of course, so aside from the height, it is implied that we all also know, from here, we also know, although it's not mentioned anymore, that G must be also a is a given value. So in terms of feet per second, no? So the acceleration due to gravity is 9.8. 9.8 is when it is used when we are dealing with meters and seconds. But since we are dealing with feet here, then we use this value 32 feet. No? So let me add a square for my S. No? So there's a 2 here. So since this is that's an acceleration due to gravity. No? Now, another given probably now that is not mentioned in the problem is that V sub I should be 0. No? So since it falls to the ground, then V sub I should be simply 0. No? Now, the first value that we are to find, so we are to find letter A. No? We are to find the final velocity of the object after it falls for a time equal to 5 seconds. No? So how do we find that? No? Now, next, another problem is what if we are to look for the height of the object, of course, after falling again for the same period of time. No? So how much will the distance covered by the object after falling for 5 seconds? And next is letter C. How far will the object travel only for this given time 5 seconds only. So we are looking for the 5th second here. And again, we can review the problem. So I'm going to call letter C as finding the distance on the 5th second only. Okay, now the first problem. So let's start with letter A. So for our solution, so letter A, how do we find the final velocity? So again, final velocity can be written as V sub I plus GT. So that's our equation. Now, our initial velocity being 0, so this will be 0 plus G, G which is 32, and then time which is 5 seconds. And then therefore, our final velocity, after 5 seconds, our object will now travel 160 feet per second. So that's how fast the object will travel on the first 5 seconds. So again, what's the direction of our object here? This object is going downward. So it's going down. And again, as it goes downward, so for the first 5 seconds, so if this is the time equal to 5 seconds, so this is how fast the object is. So after reaching this point, so it travels at 160 feet per second. Now, what about letter B? So height of the object. So how far did the object fall? So determining how far the object falls, we have V sub I T. So you multiply it with the initial velocity in the time plus 1/2 of G, and then we square our time. So again, we have this value here. Now, since again, the initial velocities are both 0, so we can literally just make that value as well 0. So because initially we know that that is 0, the value there is 0. So therefore, if we'll try to find now our H, so H will be so this basically 0, then plus 1/2 of G, which is 32, and then we square 5. So we square the time, So squaring the time, multiplying it to 1/2 of 32, which is 16. Then we are now able to find no, the distance traveled by the object after no, 5 seconds. No? So this is the distance traveled by the object for 5 seconds. So that value is around 400 feet. No? So therefore, if we'll try to measure this distance here, no, this is 400 feet. No? Its speed is 160 at the tip of this arrow. No? So again, no, I will call this as the distance traveled no, for 5 seconds. No? So I'll just call it at h5. No? Now, so the value here no, is h5. Now, if we are going to get, no, let's say I'll find no, another expression here. So what if no, we will solve the distance traveled by the object no, for 4 seconds. No? So here, no, if we will get the time for this blue colored arrow, no, then that distance is uh, covered no, only for 4 seconds. No? So in order for us to get that, no, get this value, no, so we will be able to get this by the same equation. No? So h vi t plus 1/2 gt square. No? But of course, our t here is already no, equivalent to 4. No? So this value now is 0. So since initial velocity is 0, plus no, 1/2 of 32 times 4. No? But 4 will be squared. No? And if we square that, then we'll get a different value for h4. No? Our h4 value there will be around 256 feet. No? And again, now don't forget that t here is a squared expression. No? So this is squared. This is squared. No? So therefore, what's the difference of these two heights? No? So you'll notice now that there are two heights here now that you are now able to see. No? So this is for 4 seconds. The red one is for 5 seconds. So how far did the object falls only on the 5th second? No? So that's what we are looking for in letter C. No? So this value here is actually no, the distance called no, h no, during the 5th second only. No? So how far is that distance traveled during the 5th second? And that's equals to the difference. No? So to be able to get letter C, no? So to solve for letter C, no? Which is h no? During the 5th second, then that's equals to h5 minus h4. No? And the value there, no? The distance for the 5th second is 400 minus 256. No? And that's equal to our value, no? Equal to 144. That's 144 feet. No? So again, this is a falling object. No? And again, it can travel two distances, but how far did it travel only on the 5th second? So that's merely the difference of these two distances. No? Again, to get this, we use the same equation as what we applied in letter B. No? So getting h4 and h5 allows us to find the value for the 5th second. Okay, so that's our figure here. No? So again, we try to go back to our problem. So we are done with letters A, B, and C, and let's say we try the next item. No? So a bullet is released upward from a rifle, no, with an initial velocity of 120 meters per second. And again, no, we'll try to calculate, no, the first three questions. No? So what is its velocity after 8 seconds? What is the height of the bullet after that 8 second? No? And again, similar to our previous problem, we will be looking for the distance traveled only on the 8 second. So we know that letter C will be a subtraction process again. No? So how do we get this? Then we will subtract now H8 with H7. No? Okay, so let's try to use again, no, our whiteboard. No? I think it's not there anymore. Oh, it's still here. So let me erase this one. So we are now on number 2. No? So we will only try 2 sample problems. So we start out with our given. No? So for our given, we have no, an initial velocity this time, no? Because the bullet is fired up. No? So this one will have an initial velocity. No? So the bullet will never go up unless, no, we apply, no, an initial velocity there. No? Now this time, since the object is going up, no, we will consider gravity here, no, to be negative. No? So uh, our gravity value is negative 9.8, no, meter per second square. No? So that's another given. And we need one more value to be able to calculate. No? So as I've said, you must have 3 known values, no, for you to calculate. No? So what's the first one that we will determine? Again, we will find, no, for letter A, we will determine the final velocity of the object for a time equal to, no, 8 seconds. No? And then next, we will find letter B, its distance traveled, no? And then we will still look, no, for that distance, no, given that its time is 8 seconds. And then lastly, we will look for the distance traveled during the 8th second. No? So we will determine the distance traveled during the 8th, no, second. No? So starting with our first item, no? So let's start with our first solution. So letter A, no? How far will the object, no, travel? No? How fast will the object travel, no, after 8 seconds? So for us to find that, then of course our equation will be V sub F equals V sub I plus GT. No? And again, G here is negative, no, because gravity is considered negative. No? So it's 120, the initial speed, plus negative 9.8, then multiplied by time, no, which is 8 seconds. No? And our V sub F value is, our V sub F is 41.6 meter per second. No? So that's how fast the object now will travel. So what do you notice when objects go upward? Its velocity now slows down. No? So initially, so the initial velocity of our object here, V sub I, is 120. No? Is it logical for the object to slow down when it's going up? It should be. No? So when objects go up, they tend to slow down and eventually come to a stop. No? So you cannot say that the object will continue to increase its speed. So the bullet, once it reaches now this particular height, and after this given time, this one will now slow down to only this value. No? So this is for 8 seconds. No? If we will try to find now a value here, no, for example, no, 7 seconds, then the object probably will just reach this point. No? This is the uh, height with which the object travels for 7 seconds. No? And probably the object is much faster here compared to the value of its velocity at the higher point. No? So, but the question is, no, this height here, no, the height here is known as h8, and we do not know that value. No? This one is our h7. So this is the height at after 7 seconds. No? So our letter B question is asking now for h8. No? So letter B. No? How fast, no, or how far will the object travels, no, after 8 seconds? So again, our equation here is VI t plus 1 half, no, gt square, and t there being equal to, so we square the value of time. No? So initially this is no longer 0, so initial velocity is 120 times 8, no, seconds, and then plus 1 half, and our g value now is negative 9.8, and we square the time, so our time is 8 squared. So therefore, so this one being negative will be subtracted to our value here. No? Otherwise, this one will go way too high. No? So our height now, no? We will get the value there. That's 646.4 meters. No? So the blue arrow will reach to up to a value of 646. No? Now, if we are going to go to letter C, now we need another value here, no, which is our H7. No? And again, no, for our H7, so for our H7, so after 7 seconds, no, then we have now this value 120 times 7, no, of course 7 seconds, plus 1 half of 9.8, or negative 9.8 rather, and then multiplied by 7 seconds squared. No? And our value now, no, our answer, I mean, so for 7 seconds, the object will now, no, travel to as high as 599.9 meters. No? So it will not really go very high, no, because again, no, that's for 7 seconds, but the speed here is much greater compared to the height, no, h8. No? So h8, there's less velocity, no, because again, no, as it goes higher, then it slows down. No? Now, however, now for letter C, and which is our last question to answer. So how far now is this 8-second distance? No? So again, the distance traveled for the 8th second, no, which is basically, no, this blue, no, the remaining blue value is the difference of h8 minus h7, no, which is in our case, no, equals to 646.4 minus 599.9. No? And that gives us, no, so our value here will be 46.5, no, meters. No? So again, where is this h8? No? The h8, no, of a second. So that h8 is actually this length only. No? So this is the distance traveled only on the 8th second. No? Now this one is again very similar to what we solved earlier. No? So again, this is our sample problems for our free falling body. No? So there is a lab experiment that I want you to do, no, on free falling body, which will require or asks you, no, to determine the experimental value of the gravitational pull. No? So our accepted value or the true value is 9.8. No? But we will do an activity in the lab and we will try to determine, no, how much is that gravitational pull. No? So the equation, however, that you are going to apply, no, in the lab, no, in your lab activity will be, no, our gravitational value, no, in the lab. So how do we determine the experimental value of G? No? I'll call it small letter G. No? So in the lab, to get this value, you will solve G now with twice, 2 times the height, no? And we divide it, no, by the square of the time. No? So T square. No? So this is our working equation when we go in the lab. So what are the values that you need here? So there are two things. No? So if you will try to drop an object, so you will be letting a tennis ball fall, no, in your activity. So there are two things that you need to have, no, in this activity. So if this is a tennis ball that you will have in your lab, so you will let it fall with zero velocity because you will just simply release it in your hand, no? And then you are going to get the time. No? So you will record the time here. No? So T is the time. And then you'll get the height of this object. No? So the height, I believe, no, there's the first value of the height, which is equals to 1.5, I think, meters. And you let this object fall, no, at the height of 1.5 meters, and you measure the time 3 times. No? So you will record how long, no, did this object fall. No? So you will use probably your cell phone in that case to get the time. So you will be recording this time. Since there are 3 values here, then you're going to get the average. No? So you add all 3 values and divide it by 3. No? So that's the one that you're going to use in this denominator. And for H, no, then the pre-measured height H. No? So there's a demo that I already illustrate, no, on how to get this expression. So this is on your laboratory portion. So hopefully, no, you'll be able to watch it in your groups. No? So you will be assigned groups there um, to determine your lab experiment. No? So you will pass and upload, no, your lab reports, no, in this activity. No? Okay, now we go to Newton's laws of motion, no, and we realize that the first law, no, is asking about the law of inertia. So in the law of inertia, no, if forces, no, are balanced, when we say balanced forces, the force F1 and F2 are equal in magnitude. No? So if F1 is 30 newtons, F2 is another 30 newtons, and they move in two opposite directions, then their difference is simply zero. No? We call the difference there as resultant. No? So if there's no resultant, then the body will remain at rest. No? And we call that forces as balanced forces. No? Balanced forces do not create any motion. No? So the body will continue to be at rest. No? Now, if the body is at rest, but you now apply, no, two forces that are of different value. So one is 50, another is 30. So there's now a difference of 20 newtons. And again, no, that 20 newtons will cause this body to move to the right. So from rest, this will now change its condition into motion. No? And again, no, in order for motion to occur, the forces should be unbalanced. No? So if there's an unbalanced forces, and that unbalanced force is known as a resultant, the resultant now is 20 because 50 minus 30 is equals to 20. No? So here, initially, if they're equal, then the resultant is zero. No? So again, now this one now is a condition where which we call as unbalanced force. No? So when there's an unbalanced force, the body will tend to accelerate or now cause some kind of a motion. No? So if the object is already in motion and the forces are the same, no, then the body will travel with constant velocity or uniform motion. No? So the body will not accelerate. So it will just simply move as it is. No? But if you have to apply a force with two different values, then if a body is already moving, then the body will now tend to move much faster than its initial state. No? So there are two things that unbalanced or balanced forces can work. Either it is when the object is completely at rest or when the object is already in motion. No? So here, the body will now accelerate, but here, the body will just move with constant or uniform motion. So again, this is an example of balanced forces, whereas this one is an unbalanced force. No? Now that constitutes what we call as the law of inertia. And again, our usual tendency is to remain in our state, no, where we what we are doing at the very moment. We call it as inertia. No? Now, when we apply an unbalanced force on a given body, its inertia will now change. No? So it will now cause the object to either stop moving, if it's already moving, or it will cause the object to increase its speed, and change from rest to motion. No? So that is when there's an unbalanced force. Here in this problem, the unbalanced force is also known as the net external force. No? Now again, bodies with greater mass have a greater tendency to remain as it is. No, they call it as the measure of inertia. No? Now the second law is known as the law of acceleration, no? And it is equated in this equation: force or the net force is equals to the mass times the acceleration. And usually we always explain it that more massive bodies have lesser acceleration. No? So bodies with a bigger mass tends to move with lesser acceleration. But bodies with smaller mass can increase its speed very fast. No? Like a bullet, for example, a bullet can fly very fast. No? But if you will make a bullet so big, then it cannot uh, accelerate so soon. No? So that's why they build the bullet and they make it not that large in order for it to be accelerated in such a short period of time. No? So just imagine a gun, guys, and your gun is made of bullets that are so large. Then you have to propel those bullets with a bigger gun, and you could not simply carry it. No? So you could not fire it at a very high velocity or speed or acceleration when your bullets are so massive. No? So less mass means greater acceleration, while greater mass will have lesser acceleration. No? It can accelerate relatively slower. No? So the last law is the law of action and reaction, which we say that when there's a given action, then a reaction in the opposite direction results. No? So like you step on a skateboard, if you don't know how to use the skateboard, then tendency is the skateboard will move forward, but you will be thrown backward. So that is if you don't know how to use the skateboard. So as soon as you step on the skateboard, the tendency of the skateboard is to move forward, while the person who does not know how to use it will now tend to fall back. So action and reaction. Just like in the case of a rocket, the rocket will move up because of the action of the fuel being burned down and the rocket is being propelled up. So action and reaction is also typically seen in our rockets. Now, an example of Newton's second law, which is the law of acceleration, is which is equated as F equals ma. So if you have a force of 15 newtons and there's a mass of 90 kilograms, so how much is the acceleration? Then we simply divide the force with the mass of the object. No? So the object will now tend to accelerate at 0.17 meters per second square. No? So this one, this problem is first, calculating the acceleration. And again, the acceleration can be determined by the the value of our difference in the velocity. So usually our equation for acceleration, so acceleration can be determined by subtracting vf with v sub I, and we divide the whole thing by time. So if we divide the two, so in this problem, we can have final velocity to be 18 minus initial velocity, which is said to be at rest. So therefore, this must be 0. Then you divide it by the time equals to 3 seconds. Then you have this expression, 6 centimeter per second square. Now we are going to use this acceleration and multiply it to the unit in grams. So the mass and the acceleration is multiplied. So, however, we'll notice here that our units are in grams, centimeter, and seconds. So the corresponding unit of force is known as dynes. We call this as the CGS system, centimeter, gram, second, unit. So if it is in terms of kilogram and meters and seconds, then our unit of force is in Newton. So there are two units of our force, again, in dynes and in Newton. So unit of force, so you have 1 Newton, which sometimes we write simply as N, is equals to 1 kilogram meter per second square. And another unit is known as dynes, and dynes is in terms of gram. So if you have a mass of 1 gram and the acceleration is in centimeter per second square, then you'll have a unit in dynes. Now we seldom use dynes because they appear so big, but actually the value is very small. So these are our units of forces. And again, this is a result of multiplying mass and acceleration. Okay, another example. We have a net force of 60 newtons applied horizontally on an object 40 kilograms. So what is its velocity after 6 seconds? So you can probably try this on your own. Or there's a corresponding expression also to solve it. So you can try example 3. So we have examples 1 and 2. So I think for today, we can call it as